equation of the hyperplane. This can get very interesting very quickly. And it does when I paste this nice hyperplane. This is something I now reiterate, but it turns out that a plane is determined just by the vector which it is normal to. Well, this and the height at which it stands. So usually there is some constant to think about. Intuitively, it looks something like this. You have a plane and you have this, infinite flat sheet in three-dimensional space, which we live in right now. And then there is a perpendicular vector. There's a normal vector. And that's what determines the plane. But I want you to notice that, it doesn't have to be this example. But if you just look at any plane, you'll find that you can always draw a perpendicular line. But this is the part where the constant for the height comes in. When I do like this, yes, this vector is perpendicular to this plane, but it is also perpendicular to this plane and that plane and all of these. This infinite, this also infinite level of height, this axis. So the constant really helps us determine at which floor we're at. Are we at the first floor? Are we at the second floor? So on and so forth. So this is, I hope, is good. Equation of the hyperplane looks like this, usually. So you have, this is a hyperplane, so it's 4 variables. So you take the first variable, you multiply, well, I don't need to multiply anything. I just write tx, y, z, and I take the dot product of this thing with the normal vector. So this I'll call the normal vector d. So it has some coordinates, And when I perform this, I should get, this, let's say this, I don't want to say height, but, some number, so some number for the height at which the plane lies. So I think we would like to find this vector. I think it would be very, very meaningful. Let us attempt to make some progress with the givens. I always think that the most important part of any problem is to familiarize yourself with the givens. So let's actually do that. This is our our equation. I'll immediately start replacing these terms with the actual vectors. Here I have a lambda. I'll remove the a and I put this. I do the same thing for the other variables. Well, vector variables. Alpha, beta, and gamma are just scaling constants. So I hope these do not scare you away. Yes, and I hope you don't mind if I scale the entries. So I'll get alpha here, I'll get alpha there, I'll get beta here, beta there. I'll get 2 gammas here as well. And I can even take this one step further and write it as an addition, of coordinates. So this would give me alpha plus 1. This would be just beta. This would be gamma. And this would be gamma plus beta plus Alpha plus beta plus gamma. Sorry, I'm not Greek. I don't know all the Greek letters, and I think that's fine. So we are here. I think it is fair if I equate t to this, if I equate x to that, y to this, and z to that thing. I hope this is not too horrible for you to witness, because that would be very unfortunate. Delete this part, do like this. This is equal to this, this is equal to that. Okay, remember that our original goal was to multiply out. I hope this doesn't look horrible. It looks horrible. I need more space, please. Oh no, it doesn't look that bad. So I want to remind you that the goal was to find the entries which we multiply these terms by to get a constant. The goal is to get a constant, really. I also want to remind you that if we expand this using the rules of just simple dot product multiplication, you get d1 times t plus x times d2 plus y times d3 plus z times d4 is equal to some number. So always keep this in mind. We always need this nice and constant number to be able to proceed. So that is something to keep in mind. Now let's actually do that. If we would like to get a constant here, then we would like to have things cancel out with each other. So for example, let's take z. Z has alpha plus beta plus lambda. Okay. I want to eliminate this alpha. So I'll take away t, because when I take away t, the lambda will cancel out. Okay, I also want to eliminate the beta. Then perhaps I should also take away the x. And similarly for gamma, I take away this y. Now let's see what I get. So this would be equal to alpha. I'll write it down beneath. This is equal to alpha plus beta plus gamma. The t is equal to alpha plus 1. I'll just distribute the minus, get minus alpha minus 1. Minus x is minus beta, and minus y is minus gamma. So this is great because we've effectively cancelled out all the terms, and we just have a constant. So this constant is equal to minus 1. So z minus t minus x minus y is equal to minus 1. Or in other words, you could also say that this would, in the sense, imply that z minus t minus x minus y plus 1 is equal to 0. In this case, if we go back to the perpendicular vector form, the d vector, then the d vector is just the coefficients of these variables. The D vector will actually look like this. And I would like you to actually take a moment to check this yourself. So please check that if I take the dot product of Txyz with now the coefficients. So well, z is 1, z is minus 1, x is minus 1, and y is minus 1. I would get not 0, but I would get minus 1. And of course, this equation, so I'm not sure what you would effectively encounter in the choices, but this equation is also valid if you multiply it all by minus 1. So you could, just multiply this by minus 1, minus 1, minus 1, minus 1. So you have, all of these are positive and this is negative, and then you have minus 1 here. They're really just the same thing. They contain the same amount of data. And it's just like these two statements are just restatements of each other. So they are equivalent in that sense. This should be the answer for the exercise.